Welcome to this explainer. Today, we're stepping into the matrix of Cambridge exams. I want you to completely change how you view your exams today, because here is the ultimate truth about scoring top marks in Cambridge physics. There is no paper. There are only patterns. Once you learn to see the code behind every single question, you become unstoppable. Today, we are going to build our understanding of dynamics from the ground up, starting with simple pushes and fundamental properties, all the way to complex, real-world crashes. But we aren't just going to talk about the physics. We are going to decode the exact strategy you need to conquer syllabuses like the 0625, 0651, 0652, 5054, and specifically the mighty A-Level 9702. We are going to break down the examiner's reality, looking at real past paper questions, identifying the traps that thousands of students fall into, and showing you the exact blueprint to guarantee top marks. Are you ready to see the code? Let's dive in.
Okay, let's dive into this with our first challenge. Have you ever stood outside and dropped two completely different objects at the exact same time? Say a standard tennis ball and a badminton shuttlecock. They do not hit the ground at the same time. Now, this is a classic Cambridge past paper scenario. Let me introduce you to two typical students we see all the time, Alex and Sam. When faced with this question on an exam, Alex panics and completely overloads the answer with raw physics facts. Alex writes a whole essay about gravity, orbital mechanics, and historical Galileo experiments, but includes zero actual analysis of the objects in the question. The examiner's red pen just slashes right through it. Then we have Sam. Sam is always rushing against the clock. Sam writes one messy sentence. Gravity pulls them, but the shuttlecock has feathers. Sam completely misses the specific command word requirements and gets maybe 1 mark out of 4. To the untrained eye, gravity is just gravity, right? But the reality of motion and the reality of exactly what the examiner wants from you is far more beautifully complex. To solve this puzzle, we first have to strip away some everyday misconceptions and build our physical toolkit.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, the first tool we need is to fix a very common mix-up. People use the words mass and weight interchangeably all the time, but in dynamics, they are totally different beasts. And this is exactly where we need to reveal our core strategy. When an exam asks you to distinguish between mass and weight, you need to understand the command word distinguish. You can't just define one, you have to explicitly compare them. This is where top students use the Peel framework. Point, evidence, explanation, link. Your point is that mass is a base quantity measured in kilograms, representing the fundamental property of an object that resists any change in its motion. It doesn't matter where you are in the universe, your mass stays exactly the same. Your explanation contrasts this directly with weight. Weight is a force. It's measured in newtons, and it represents the actual gravitational pull on that mass. They are connected by the simple equation, weight equals mass times the gravitational field strength. For instance, a 100-gram mass has a weight of nearly 1 newton on Earth's surface. But if you take that exact same 100-gram mass to the moon, its weight plummets to just 0.16 newtons, because the moon's gravitational pull is only about a sixth of the Earth's. The mass resisted change the exact same way, but the pull was weaker. See how that hits every mark on the rubric?
Now that we know what mass truly is, we can introduce the absolute engine of dynamics, momentum. Represented by the letter P, momentum is defined simply as the product of mass and velocity. But do not let that simple equation fool you. Let's look at another common trap. An exam asks, explain why momentum is a vector quantity. Alex will just write P equals mv, 0 marks. Sam will write it goes in a direction, maybe 1 mark. The Peel framework demands more. Because velocity has a specific direction, momentum is fundamentally a vector quantity. It strictly cares about where an object is heading. Think about a 2-kilogram object traveling at 3 meters per second. It has a momentum of 6 kilogram meters per second. If it travels at the exact same speed but in the opposite direction, its momentum is -6. The sign matters completely. To give you a sense of scale from our source material, imagine a massive cruise liner with a mass of 20,000 tons traveling at 6 meters per second. That ship carries a staggering momentum of 120 million kilogram meters per second. Trying to stop that is where our next concept comes into play, and it's where we'll see our students really transform their answers. You literally cannot talk about motion without Sir Isaac Newton. His 3 historical axioms govern absolutely everything moving around us. And here is where we enter the transformation phase. We're going to take those red pen marks and turn them into green check marks using the physics success blueprint. First law, an object will remain at rest or keep moving at a constant velocity unless acted on by a resultant force. This is surprisingly counterintuitive. On Earth, we falsely learn that we need force to keep things moving because we constantly battle friction. But in deep space, a rock will glide in a straight line forever until it hits something. Second law, force is formally defined as the rate of change of momentum. And third, if object A exerts a force on object B exerts a force of equal magnitude, but in the exact opposite direction on object A. When Cambridge asks you to state Newton's first law, you must include the phrase resultant force, or net force. If you just say, unless a force acts, you lose the mark. It's that precise.
So, the crucial point here is how we translate that second law into something we use every single day, and more importantly, how we calculate it on the paper. If force is a rate of change of momentum and mass is constant, the math beautifully simplifies to F equals ma, or force equals mass times acceleration. This elegant equation perfectly illustrates what we just talked about. Mass is the resistance to change. If you apply the exact same force to two different objects, the one with the larger mass will have a much smaller acceleration. Let's look at an application. If a car with a mass of 1.2 tons needs to accelerate from 5 to 30 meters per second in 7.5 seconds, we can use F equals ma to calculate that it requires a constant accelerating force of exactly 4,000 newtons. But watch out. Here's where Sam loses marks. Sam calculates 4,000, but forgets to write newtons at the end. In the Cambridge grading matrix, missing units means dropping a mark. Every single time. You have to be meticulous. You have to see the pattern.
And this brings us to an image that brilliantly illustrates Newton's third law, which might just be my absolute favorite. Consider the child jumping off the wall here. We easily understand that the Earth is pulling the child down with a gravitational force. That's their weight. But what we almost never think about is that the child is pulling the Earth upwards with an identically sized force. Because the Earth is so unimaginably massive compared to the child, its acceleration is completely negligible. F equals ma at work again. But the force is unequivocally still there. It's an equal and opposite interaction, no matter the size difference. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome to our interactive workshop. We are putting 60 seconds on the clock right now. Challenge 1, data scan. Look at this complex physics chart. It's a speed-time graph tracking a shuttlecock and a tennis ball falling from rest. I want you to extract the core trend before the timer runs out. Ready? Go. Look at the lines. When they are first dropped from rest, both the tennis ball and the shuttlecock have the exact same steepness, the exact same initial acceleration, which is gravity, but almost immediately their paths diverge. Why? What is the trend? The trend is that the shuttlecock's acceleration decreases much faster than the tennis ball's. Time's up. If you spotted that, you are thinking like an examiner. It comes down to drag, or air resistance. Air resistance isn't constant. It depends heavily on an object's shape and its speed. A streamlined object cuts through the air, while a non-streamlined object, like the feathered shuttlecock, faces a massive, turbulent fight against the atmosphere.
Let's break this journey into 3 precise steps that will guarantee you full marks on a describe and explain question. Step 1, at the very beginning of the drop, drag is negligible. The resultant force is just the weight pulling down. Step 2, as the object speeds up, the drag pushing up increases. The resultant force gets smaller, so the acceleration decreases. This is why the curve on our graph starts to flatten out. Because the shuttlecock is lighter and less streamlined, this upward drag becomes significant compared to its weight very, very quickly. Step 3, eventually the upward drag perfectly equals the downward weight. The resultant force is exactly 0. Newton's first law takes over. The object no longer accelerates, it falls at a constant speed called terminal velocity. The shuttlecock reaches a much lower terminal velocity much sooner, which is exactly why it hits the ground long after the tennis ball. If you use the Peel framework to structure those 3 steps, you have literally hacked the marking scheme. Now that we've mastered how individual objects behave when forces act on them, it's time to smash them into each other. This brings us to challenge 2, find the flaw. I am going to read a sample paragraph, and you have to identify where the student is losing marks. Here it goes. The principle of conservation of momentum states that the total momentum before an interaction is equal to the total momentum after the interaction. Did you catch the flaw? Did you see the missing code? The student completely forgot to specify in a closed system or provided no external forces act. Boom, mark lost.
Because of Newton's third law, those equal and opposite internal forces, we know that in any closed system where no external forces are interfering, momentum is completely conserved. Momentum is never just lost, it is meticulously accounted for and transferred. You have to include that condition to get the full marks on the 9702 syllabus.
What's really amazing is how robust this principle is, and how Cambridge loves to test it. It applies perfectly to a one-dimensional head-on collision. If two objects are moving toward each other, we assign one direction as positive and the other as negative, tally up the total momentum, and use that to perfectly predict their final velocity. But for you A-level 97002 students, you know it applies equally well to glancing, two-dimensional collisions, like discs sliding on an air hockey table. In these cases, because momentum is a vector, we simply resolve the momentums into perpendicular components. The total momentum parallel to the original movement is conserved, and the total momentum perpendicular to it is also conserved. The math is a bit more involved, requiring some trigonometry, but the fundamental law stands totally unshakable. If you map out your x and y components clearly, the examiner has no choice but to give you all the working marks. While momentum is strictly conserved in every type of interaction, the same cannot be said for energy. This distinction is incredibly important for diagnosing crashes, and it brings us to challenge 3, speed writing. You have 30 seconds to write down the exact difference between these two. We divide collisions into 2 categories, elastic and inelastic. Go. How would you structure this? In a perfectly elastic collision, both the total momentum and the total kinetic energy are conserved. Nothing is lost. But in an inelastic collision, momentum is still conserved, always, but the total kinetic energy after the collision is less than it was before. Some of that kinetic energy is converted into other forms. Time's up. If you clearly separated kinetic energy conservation from momentum conservation in your answer, you nailed it. That is the exact discriminator the exam board uses to separate A-grade students from the rest. Now, let's look at the final system. We have 3 rules that guarantee top marks: command word decoding, Peel framework application, and the time management matrix. Let's apply this system to these 2 images. When a massive golf club strikes a golf ball, we have a nearly perfectly elastic collision. In a perfectly elastic interaction, the relative speed of approach equals the relative speed of separation. If the club approaches at velocity v, the ball rockets away at nearly 2v. The kinetic energy is preserved as motion. But compare that to 2 trolleys colliding and sticking together. This is a classic inelastic collision. Let's look at the data. 2 gliders collide and stick. Their combined kinetic energy before the crash was 1.8 joules. After they stick together and lazily drift off, their kinetic energy is just 0.054 joules. The momentum remained exactly the same, but almost all the kinetic energy is gone. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. Which leaves us with this final burning question to test your new analytical skills. If momentum is strictly conserved in every single crash, but the kinetic energy in an inelastic crash plummets from 1.8 joules to a tiny fraction of that, where exactly does the missing energy go? Energy cannot be created or destroyed. So when those trolleys slammed together and stuck, what new forms did that energy take? Think about the loud sound of a crash, the heat generated by the intense impact, and the physical deformation of the metal. The physics of motion isn't just about moving. It's about the incredible transformations that happen when motion abruptly changes. And understanding that is how you conquer the Cambridge matrix. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.